Alright, let's work on the second problem of the day, which is going to be LeetCode number 146 LRU Cache. Design a data structure that follows the constraint of a least recently used, or LRU, cache, with a couple of parameters. Well, we need a constructor that passes in a capacity. We'll need a get, which will return the value of a key if a key exists, otherwise we return -1. And a put, which updates the value of a key if it exists, and otherwise adds it to the cache. So I guess the good thing is that this problem showed up on my radar a while back as one of those Amazon tagged questions that they seem to ask very often. So I've had some time to think about the solution here, and I think it makes sense, but I'm going to walk through it sort of step by step to sort of reconstruct, I guess, at least the rationale behind the solution. And maybe I'll hit some roadblocks along the way as well, and in which case we'll have to address those. But first, the main constraint is that all operations, well, all two of them, the get and put, must run in constant time. The problem then becomes this. When we add an element into our cache, we need to add it such that let me think about this a little bit. Sorry. When we update an element within our cache, we need to figure out how to move that item from its current position in the LRU sort of queue, I'll say, to the back, right? So all the items within the LRU cache will mature at the same rate. And what I mean by that is that the oldest element, the least recently used element, and the second least recently used element will not change in terms of their position so long as neither of their elements of their values are updated. However, if an element is updated, then we need to consider moving that element to the back of the least recently used queue. In terms of adding an element, we just add it to the back of the queue. No problems there. So this is our main problem to solve. It's not adding an element, it's updating an element. And the main problem is not that it's not possible or it's that it's difficult to do, but it's that we need to have this run in constant time. Of course, if we did, like, the most naive solution would be to just have this in an array of some sort. We could do that. And we can move that to the back of the array and like shift the elements and all that stuff, right? But that wouldn't be constant time performance. The only thing, or the main data structure that comes up, I guess, when you think about how do we move elements within the list, given an element in the middle of the list, how do we shift it to the back in constant time? So shifting elements from some middle point to the back, that seems to signal a linked list implementation. And the reason is that if we know what node is behind it, and we know what node is in front of it, well, we can link those two. we can link the previous nodes next to our next node, our current nodes next, and our next nodes previous to our current nodes previous. So now we have a free node, our current node is free, and now all we really need at that point is just another reference to the tail of the linked list, right? And once we have a reference to the list tail, then we can just simply set the valid parameters. So the tail's next is our current node, our current node's previous is the tail, and then after that we set the tail to our current node. I believe that there is a linked list implementation within Java, though I do not know if it actually is a doubly linked list. Cool, it turns out that it is. That is great news for us, because that means that we can use the linked list implementation from Java directly without having to code our own implementation of a linked list. Though that might be useful for some practice later on down the line. Well, the secondary problem in this case is, okay, let's use a linked list. How do we figure out the position of the item that has the key that we want, right? Because within a linked list, we don't have access to all of the elements, right? In terms of, if we had it in terms of an array, like we said before, then we could simply index into the array, right? Because it is a contiguous segment of memory. That is not the case for a linked list. So there's no native way within a linked list to keep track of all of the elements in terms of where they are. We don't have a way to sort of hold their reference natively with just a linked list alone. This is where a hash map comes in. The entire reason why we decide to use a hash map in this case is because we can very easily link a key to a reference to a list node, right? So that way, when we ever get a key, we can instantly get the reference to the node, and using a doubly linked list, we can get a reference to the previous and the next pointer. Of course, this would not work if we were dealing with a singly linked list, because there would be no way to link the previous pointer to the next pointer, to the previous node to our next node, with just the reference to our current node. Of course, there may be other ways to deal with that, but with a doubly linked list, it's just very, very easy compared to a singly linked list, right? Because you can just take the previous pointer or the previous reference of our current node and link it to the next reference of our current node. So that's what we'll do. So our solution here will use a hash map of int list node, which will hold a reference to any given list node with a key. We'll have a linked list, which will allow us to move items from some arbitrary middle to the end if we decide to update. And of course, the last sort of piece of the puzzle is our capacity. In terms of our capacity, we will just hold an integer variable, or this will be an integer. We can just have a current capacity which is an integer variable, that when met will simply take or turn all puts into replacements. And what this replacement will do is that it will remove the last item, or rather our head, I guess in this case, and it will add in our new node at the tail. All the other items are really unaffected in that case. I think in a more memory sort of efficient solution, we could also potentially reuse the node. But at the same time, reusing the node has its own implications because we don't necessarily want to introduce side effects into our nodes, right? We want to keep them as sort of read only once we've initialized them, just to make life easier. Let's see. So this creates a linked list of elements E. So we'll have to introduce our own list node class. So let's start coding up our solution. So let's do a list node class. This will have a val. I mean, what really is the purpose of this node? Well, it must have the following items if we want it to be a doubly linked list, right? We need to add a previous element. We need to add a previous, or let's add a value, which is an integer. We need a previous, which will be a variable, which will be of type list node, and a variable next, which will be a list node, also nullable. We'll have a current capacity set to 0. We'll create an index, or a reference map, we'll call it, is a mutable map of integers to list nodes, because the integer is the key. We'll need a linked list of type list node. We'll also need a variable for our head, which is of type list node nullable, which will start as null, as well as our tail, which is nullable. So now we can say, at least for our get implementation, this is pretty simple, right? So if our reference map contains our key, or rather get our key is not null, then we can return return our reference map get key. So this will be the entry. So this will be the list node dot value. Pretty straightforward stuff. Now, well, the main thing that I'm not sure about is this right here. Else return -1 if the key doesn't exist, right? That's part of the spec. So now we have a put. Well, we can say if, or we'll use a when case, current capacity is 0 when current capacity is equal to capacity. So evict case, add case, add and set head case. So what we can do here is that when our current capacity is 0, then what we will do is set our head to, and we're going to need a new list node, right? So val new node is equal to a list node. Our value will start off as value. Our previous will start off as null, and our next will start off as null. We'll set our head to our new node, and we'll also set our tail as our new node, and then list add. Well, actually, this list add will be at the end. So in the case that our current capacity is 0, that means that we have no elements within our LRU cache, and therefore we should set our head and our tail pointers to the node that we're just adding. In the case that we are at capacity, we need to check to see, let me think. In our evict case, what we want to do is to set our head is equal to head dot question mark dot next, and then list dot remove, or we can just do pull, I think. Then we can do list dot add. Does add, let's see. Add adds it to the end, which is what we want. Our new node. But before we do that, if we are at capacity, well, actually in both of these cases, if we add a node, well, what's the shared logic here? If we add a node, or if we add a fresh node, or if we replace a node, we want to set the tail. If the tail exists, we want to set the tail's next to us. So that seems to be actually a shared situation. So if current capacity is equal to capacity, otherwise in this case we do tail question mark dot next is equal to current capacity, or not current capacity, new node, and then new node question mark dot previous is equal to tail, and then finally tail is equal to our new node. If this is the case, if we are at capacity, then we need to remove the most recent item. Of course, we should also remove their key. In in that case, we'll probably also want to include their key in here. So that we know from the node which value to evict. So in that case, this new node also needs a key. And then we would do our reference map dot remove at list. We can say val old. We could do this, right? List dot peak and is this nullable? Yes. Dot key. So we take the first element, we take the key of the element, and we remove it from our reference map. Then we move the head reference for us. And then we remove the item from our list, and then we add our new item to the end. So this is the evict case. Otherwise, we just go ahead and do our regular case where we add it to the end. We add our node to the end. We set our tail, if we have a tail, the next value to our new node. And we set our new node's value to our old tail. And then finally we set our tail to the new node. We also should, in our reference map, and this could probably be here, after the when statement, that we update our reference map and we put inside our key will be our new, or our key, and our value will be our new node. So this is what happens if we have a completely new node. We either have nothing inside, in which we set the head and the tail to the new node. If we are at capacity, we'll remove our current head from both the reference map and then our list. And then we add our new node to the tail. And we add that reference in here. Well, what happens if our node already exists, if our key already exists within here? Well, we can say if reference map dot get key is null, then we will do this. Otherwise, we do something else. And also, let me think. We can add this to the end. Because in both cases, whether we have items in the list or not, we still want to add the new node, but we just want to make sure that the references are updated. So let's do this. That's fine, that's fine. Yep. Cool. Now, we get to the situation where our item already exists within here. Well, then we have to consider adding our item, or moving our item to the end. In that case, then what we need to do is to say val node is equal to reference map get key. Hopefully this is non-null. If not, then we'll have to force it with a double bang operator, because we know that in this case, because we've checked it in this above if statement, that this is not null. We'll say that our node.previous is equal to our node.next, and our node.next, or our node's previous next is equal to our node.next, and our node's next, the next node, the previous reference to that will be our node previous. Then we want to say our tail.next is our node here, and our tail, and our node.previous is equal to our tail, and then our tail becomes our node. And in this case, we also want to change our value. So unfortunately, we'll have to use var there. So we'll first start by setting the node.value is equal to value. This new value. We'll update the value. We'll set the previous is next and the next previous. We'll update our tail pointers. We also need to set our nodes next now to null in order to avoid creating a cycle back to the original. And I think that's it for that. There's probably a way to condense this even further now that I realize that the value should be mutable. You could probably condense this if case of replacing an item or putting an item in the middle with this eviction case, maybe? Potentially. But I'm going to leave it at like this. So we've checked all three cases. We've checked the case where the list is empty. We've checked the case where the list is not full. We've checked the case where the list is full and we need to evict something. And we also checked the case of whatever, if like whatever happens, it doesn't really matter the capacity if the item already exists. Of course, now that I say that out loud, I just remembered that we need to increase our current capacity, otherwise we'll never hit the other cases. And we want to make sure that this only happens here. Actually, we could do it here. And we say if current capacity is less than capacity, then we increase it. Because we know that we're adding something in this case because it doesn't exist within our list. Or we might be replacing something, in which case it doesn't really matter. We'll just increment it as long as it's under capacity up to that limit. And yeah, we could also do like current capacity dot coerce into a lower limit of, or whatever is the minimum of current capacity plus 1 and capacity. Or rather between 0 and capacity rather would be the coercion method. But I think that works. So let's go ahead and toss a run, and let's see if we have any issues. This is a complex expression. Capacity is not defined. Okay. We'll do this as list node. Capacity is not valid. Unfortunately, this node is not getting what it needs, so we'll slap that double bang operator in there. Because we know that this will exist. This has to exist because we already checked to see if reference map get key is null. So this code block shouldn't ever execute if this is null. And it seems like capacity doesn't exist. I wonder if it's because this is not declared as a val. Could I be cheeky and modify the class signature? Let's see. Infer type is int, nullable. Let's see. We know that this is not null, so we can get rid of that, right? We know that this is not null, that it cannot be null, because we've checked that this is not null. Let's see where we go wrong. So put get. Put and then get again. So let's see. When we add 3, here, it should evict the key, but it doesn't seem to evict the key. Let's see why. It should remove it if current capacity is equal to capacity. If current capacity is greater than or equal to capacity minus 1. Because that means that we are 1 off. We are either 1 off from capacity No. But this only should happen if we are at capacity. So this is incorrect. We create an LRU cache of size 2. When we add the 3 into here, it should go into this. Well, this doesn't exist within our key. And so we go into this else case because current capacity is not 0. Then current capacity should be equal to capacity at this point. But I guess not. Interesting. Because otherwise it would have removed it. Let's see. Why is the least recently... So the least recently used key is 2 because of the fact that 1 was gotten. So this get function is actually a little bit more complicated than I expected. So we also need to update the values here. So in that case, what logic do we actually need from here? Node is equal to reference map get key as list node. Let's create a helper function. We'll say move to back. And what do we need here? We'll need a node, which is a type list node. We'll need the tail, which is of list node question mark. I think that's it, actually. So we take this and we move this here. And this returns nothing. We don't need it to return anything. And then we say move to back. We need a node, which is our current node, and our tail, which is that tail. And then we can just do move to back node tail here as well. And here we set the value before we move it. And here we don't need to do anything. We just need to move it to the back. And thus, it should work. Tail cannot be reassigned. Right. Because that's not in... That's not in here. Well, actually, no. If we put it in here, and we can even make this private if we wanted to. We don't even need this tail because we get the tail reference from here. So there's no need for that. We just need to move this list to the back. And we don't need you. We don't need you. Let's see, when we move a node to the back, well, if node is our head, we should probably remove that. I think that might be what's happening here. Still no. Let's see. No, we want to just move the head to the head next, rather. Not just to the nodes next. Well, it doesn't really matter because the head is the node, right? So this realistically shouldn't matter. But still this right here. Interesting. Node is equal to head. Then we set the head to the next node. But then when we add this put here, we still get bonked on probably the 1, right? Let's see. Print line tail, print line head, line after move to back, Oh, it probably doesn't like the fact that it probably has a really, really tight limit on, on the runtime, to the point where you can't even debug with print statements. Okay. That is unfortunate then. So we're just gonna have to manually debug this. I didn't expect this to be so difficult, but let's see. Get this, and then we put 3 into there. When we remove, is this remove? Key. Which should work. Let's see, this get. We get this node, we move it to the back. I wonder, what if we did like a reference map remove list peak, or put list peak key -1. if list.peak is not null. Null. Let's see. I can manipulate this to do what I want. If I did this, so 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. Let's see what happens to the 1. Does the 1 still get evicted? Okay, so the 1 got evicted. Why does the 1 still get evicted? Let's see. Reference map get key is not null. And it's not, because we have it here. Unless we forgot to reference map it somewhere else. No, but the reference map is here. But this reference... Let's see. I take this node. This is 1 and 2. The head is at 1. Node should be equal to head, which is the whole reason why it gets popped. So we move the head to node's next. But apparently the node next becomes itself. The node previous next. Man, I really wish that I could just print it out, but So this had no tangible effect on actually the output of our... Yeah, it had no tangible effect on our output. What if we did this? Or let's do a reference get at 2. Interesting. What if I did this? Still returning the same issue. Even though when I do this get, what if I just do like here, like head is equal to reference map get to. Still absolutely no effect. That is strange. This should be there. If head is node, head node next. Just want to sanity check that I'm not going crazy with this test case. I just wanted to return something different. Okay, there you go. But the head value is just not changing the way that I'm expecting. Like at all. Let's see. Tail, let's see. Oh, it might be here. We add the head and the tail. Otherwise, we set the tails next to new node. No, but it should be there. And new node's previous is tail. And tail is equal to new node. I don't know why this is not working. Because this is list poll, not list remove at. So we can't just poll the list. We kind of need to just remove it out of existence. But how do we do that then? So we can't use list poll because that'll just remove from the front. Unless we do some swapping thing. But that doesn't seem fun. Yeah, so it was that polling thing. Oh my god. That took way too long. We remove it. We move the head to the next value. We don't want to do list peak. It's head key that we want to remove. But how do we just like get rid of it? Head next prev is null. Head. So we need to clear the, we should probably clear the reference there as well. And then we could probably do val temp is equal to head next. which is a list node nullable. We can say temp previous is null. We can set the head next is null, and then set the head to temp. So this is just making sure that the connections are broken, and then we just remove it. I guess that works, and then we just leave it for GC to handle it, garbage collection in Java. Not sure if I really like that outcome though. I mean, it works. We just leave it for garbage collection to deal with it. I guess in a language like C++ or something like that, we would just deallocate that memory, right, and just set it to null pointer, and then deallocate that memory manually, like with like a delete. But I guess in this case it's not really necessary because we're using a garbage collected language like Java / Kotlin, running under the JVM. Ooh, it looks like we still have a wrong answer though. Let's see. What did we get wrong? Initialize, then we put this value, then we get this value, which is fine. I don't think that changes anything. Then we put this value in. Then we get this value. When we put this in, well, if we get that key, which is 2 or 3, that's a null. When we get that key of 3, that's null. We know the capacity is at 1, so it goes into this else case because capacity is not 0. Then current capacity is equal to capacity because 1 is equal to 1. Then remove the reference map at this value. And then we break the connections. And we set head to null. We set head to null in this case. I guess we could say if head is null, then head is equal to new node. Tail was unaffected. Tail is unaffected by this change. Oh, we have a self cycle, don't we? Tail next is node, so we set the nodes next to itself. Then we set the previous of the node to itself. I guess we could say if tail is not equal to node. Actually, if tail is equal to node, then we just return. We don't need to do anything here. But I don't think that changes the problem. I don't think that fixes it. It might, but I don't think so. I think there's something different here. We put get and then we put, so we can get rid of this last get because it's not important. The idea is that when we put something in with 2, 1, then we get it with 2. Then we put something in again with 3, 2, and then we get 2 again. Then this should return -1 because our capacity is 1. And thus we should remove it. Well, we shouldn't move head to null in that case, if the tail is equal to the node. And that should be correct. Man, this problem turned out to be way more insidious than I imagined, and we're not even technically done. Well, there you go, now we're done. Man, that took way longer than I expected. I guess even if you do know the answers, sometimes it just takes a while. But yeah, ultimately the solution is to use a hash map in order to get an O of 1 time to get the reference of the node, then use a doubly linked list so we get a reference to the previous and the next, so that we can move the node to the end when in constant time as well, without affecting any of the other elements essentially, which is why we use a doubly linked list. But in any case, I hope you learned something, and I'll see you for the next problem.